So every n pi, this function will be 0. All right. So I can now look at what we had here. So this was our time domain. When we did the Fourier, we often call the Fourier domain frequency domain. If you're in the math department, you're always going to call it Fourier. If you're in the engineering department, you're almost always going to call it frequency domain. Mean the same thing. So I know that this is tau times the sinc. Oh, there should be, that's not something, it's sinc. So I can plot this. So what's the value going to be here at 0, at omega equals 0? 1, that's right. 1 times tau, so it'll be tau. Isn't that weird? So what omega equals 0? What does that mean for an electrical engineer when you say omega equals 0?
DC.
DC. When you ask a mathematician what does DC mean, what do they say? I don't know what the heck you're talking about. Now at least a mathematician that teaches engineering math, they say that's just an average. Right, signal average. Well, what's the signal average of this signal? Where did my tau come from then? I thought we were going to make a brilliant observation, but I don't see where the tau comes from. We actually have to do it right. The integral from minus tau. Right, how do we do the average? 1 over TP, TP, x of t, dt. And it doesn't become 1, does it? So I have to wait till Monday until I can come back and figure out why this isn't working. Sorry. Just, applying the conventional is that at DC, that's omega equals 0 is DC, and that should be the average of the signal. If I do the average of the signal, I get a 1. I don't get the tau. So I don't know where the tau comes from. So let's try to get back on track. What about the 0 crossings? where the zero crossings. I don't want to go anywhere. I want you guys to tell me. I'm going to make a mistake. So what do I know from here? For the zero crossings.
1x equals n pi.
Yeah, n pi, right? So we know that n pi is equal to the argument. Here's the argument. Omega tau over 2. Solve for omega. Two n pi over tau. Okay. So this first zero is going to be at n equal 1. N equal 1, I end up with 2 pi over tau. So that's 2 pi divided by tau. And then this is a symmetric function, right? So this is going to be minus 2 pi over tau. Now when n is equal to 2, I get 2 times 2, 4. So that's 4 pi over tau and minus 4 pi over tau. Right, so forth and so on. Relationship between the time period and the frequency 0 crossings. This relationship. Make some observations about the relationship between the width of the pulse and the zero crossings. As tau gets bigger, what does that mean in terms of the width of the pulse?
It gets bigger and bigger.
It gets bigger, so it's a longer pulse in time. What happens in the frequency domain?
Isn't there more zeros if the width is long?
Yeah, that's an equivalent way of saying it. What happens is this gets shorter, right? I'm dividing by tau here, right? Tau is my period, right? So, not my period, I should say my on time, right? That's how long the pulse was on for. If it's on for a long time, it's a big number. It's in the denominator, so you're dividing by a bigger number, right? So you end up with for a long time pulse, something like that. Function omega, because I'm dividing by a bigger number.